project, our main goal is to develop an automated system that can classify graphite particles based on their purity levels, 92% and 97% carbon content. This idea was inspired by our collaboration with Bogala Graphite Lanka, where we observed that the current sorting process is done mainly by manual hand sorting, which depends heavily on visual judgment by workers. In other countries, sorting is done using chemical and thermal laboratory methods such as high temperature volatilization and chemical assays. However, those methods are time-consuming, expensive, and labor-intensive, making them unsuitable for large-scale production. To solve this issue, our project introduced a modern automated approach using machine learning and image processing. In particular, we use a Convolution Neural Network, which is a type of deep learning model especially designed to understand and recognize patterns in images, similar to how the human eye and brain detect features. The CNN analyzes images of graphite particles and classifies them accurately based on their purity. By using this method, we can reduce human labor, save time and cost, move toward a fully automated graphite sorting process.
To begin, let's look at our materials and methodology. Our initial dataset was built on images captured from 92 and 97 graphite samples using a DSLR camera, which is initially contained 349 92 samples and 560 97 graphite samples. But our initial dataset was little bit unbalanced and less amount of images were captured. So to build a robust and accurate model, we knew that we needed more data. So we use data augmentation techniques like enhancing brightness and contrast and rotating the images into different angles to expand our dataset nearly to 1500 images. This crucial step helped us create a balanced dataset between two classes as well as prevent our model from overfitting. Moving forward with the detailed methodology, as the flowchart shows, the process was straightforward. We cropped the images from 7900 by 5300 to 4000 by 300, and then we applied the augmentation. And after we use the transfer learning technique and use exception model as the pre-trained model for our purposes. And then we classified the graphite into 92 and 97 based on their purity. The results were fantastic. We achieved our model accuracy as 95.95%, that is over 95, which is a good result. And here you can see in the top left corner the parameters of the exception model that we use, and right side of the slide represents the accuracy and loss curves during the training and validation purposes. Here we tried out 15 epochs and we finally thought to use 6 epochs since we can achieve the same accuracy within these 6 epochs. Our final design came after a careful process of evolution. We didn't start with the single particle sorting because our initial idea was to use segmentation to classify multiple particles at once in a bulk flow, since we can experience the same scenario at the industry. We tested several approaches, installed segmentation modules like mask RCN, but they were ineffective because they are trained on common objects, not specific minerals like graphite. On the other hand, according to the literature, we cannot use mask RCN for fine-tuning our model since it requires high-capacity computers. So otherwise, it may take a few days to train the model. Other methods like SAM either broke single particles into multiple fragments or were highly sensitive to lightning and particle overlap. It leads to low accuracy. It became clear that this approach was not reliable enough.
Let's move into the design evolution, from segmentation to single particle sorting. but our final decision was to shift to a single particle sorting system. This approach proved more reliable and achieved an accuracy over 95%. As you can see here, this is our proposed hardware design prototype. This was done by using SolidWorks software. So as you can see in part A, it's the whole complete design. In part B, you can see the upper bin with the load cell and actuator plus the doors. Part C, you can see the sorting table with a stepper motor. Finally, D, the lower bin connected to the tube. At the very end of the tube, we propose to insert a sliding door with a laser sensor. All these hardware, sensors, and also the CNN model connected via Raspberry Pi platform. So let's discuss about the system components. So in here it includes a conveyor, 2 bins from the conveyor with the weight sensor, which means the load cell, a tube connected to the bin with a laser sensor triggered sliding door, followed by a camera setup with the CNN model and a rotating stage to sort particles into 2 different bins. So let's discuss about the key features. The key features are, this design is a simple one, cost effective, time saving, and also very easy to maintain. Though there are some key features, there are some limitations when it comes to the reality. The current model is designed only to sort a single particle at a time. And also there is a limitation which the true lighting condition which we train the model is really required when it comes to the practice. And also the segmentation modeling needs a high power computing capacity. And finally I can say that this complete hardware design will cost actually around 70,000 to 100,000 Sri Lankan rupees.
Moving on to our suggestions and future work. To enhance our proposed system, we first suggest installing 5 or 6 prototype units across the graphite processing plant. This would increase throughput and allow testing under real industrial conditions. We also recommended linking all prototypes to a central monitoring system to collect data in real time, helping operators track accuracy and efficiency. For future work, our next step is to build and test the full hardware configuration using the Raspberry Pi load cell and sensors that we designed. We also plan to improve the segmentation model with higher capacity computing so the system can sort multiple particles simultaneously. Finally, we hope to extend this same model to other mineral industries in Sri Lanka. Include the project. Our work developed a CNN based model capable of classifying graphite by purity 92% and 97% with over 95% of accuracy. After testing different approaches, we found that moving from segmentation to single particle sorting procedure, higher precision and faster processing. The proposed hardware using Raspberry Pi sensors and automated sorting mechanism offers a low-cost, scalable and reliable solution suitable for local industries. Overall, this system shows how AI and image processing can modernize mineral processing, reduce manual labor, and improve product quality.
Would like to take a moment to express our sincere gratitude to all those who supported us throughout this project. First and foremost, our heartfelt thanks go to Dr. Asen Fernando from the Wayama University of Sri Lanka, our external supervisor, for his continuous guidance, valuable feedback and encouragement. His advice helped us refine our approach and stay focused on our objectives. We also to extend our gratitude to our internal supervisor, Dr. Sureka Trichampulam from the Department of Resource Engineering, University of Moratuwa, for her valuable insights, constant motivation and support during the stage of the project. We are equally thankful to the students from the Department of Nanoscience Technology, YM University, for their cooperations and for sharing resources that contribute to our process. Finally, we are special thanks to Bogala Graphite Lanka PLC for their enormous support in providing graphite samples and allowing us to engage directly with the industrial process. Their contribution made our design practical and meaningful. The reference shown here represent the key research works that guided our study. They include studies on conveyor designs, mineral image segmentation, and graphite purity identification using deep learning. Those work gave us the theoretical background and direction to build and validate our own model. We are sincerely appreciate the researchers whose findings helped us shape this project. That brings us to end of our presentation. On behalf of Group 14 Granulants, I did like to thank our supervisors, the faculty, and all of you for your time and attention. Thank you very much.